Hi, I'm Haoling Zhang, the first author of conference paper Evolving Neural Networks Through a Reverse Encoding Tree. Here, I will introduce our work. This work was initiated by Living System Lab at King Abdullah University of Science and Technology, and led by Prof. Jesper Tegner. It is also a joint work between BGI, KAST, Georgia Tech, Karolinska, and Oxford. This presentation is divided into 5 parts: introduction, movement and our proposed, experiments and result, conclusion, and acknowledgements. Our work is based on NeuroEvolution. NeuroEvolution is a combination of artificial neural network and evolution strategy for optimal effective topology of neural network to solve specific tasks. It is not limited by gradient at all and can jump out of local optima. In addition, it can create neural networks with diversity generative as a biosystem. Its basic process has 3 steps: evaluate, select, and evolve. Then it repeats itself. The reason why we focus on NeuroEvolution is that after training, we found the finite topologies could distribute or imply the cancellate from inputs to outputs. Therefore, we are interested in topologies can deduce natural formula after training. Before we discuss this deducing possibility, there are some works we need to do. Can we propose more effective strategies for obtaining topologies? For more complex problems or noise, how can we create a castle topology? In this work, we proposed an evolutionary strategy to obtain topologies faster based on a customer tree-based search named Reverse Encoding Tree. In general, Reverse Encoding Tree is a searching way combined with local search and global search. Its core technology is to divide the whole population into several clusters based on the difference between each 2 individuals. Then evaluate each cluster by correlation coefficient. Finally, to evolve individual by global search or local search selectively based on the evaluation results. Using reverse encoding tree, the population can ignore small peaks, also local optimas, which accelerates the population evolution speed. In the field of neural evolution, a neural network is regarded as an individual. If the population size is n, the number of initial or saved individuals in the population is the square root of n. As the individual will be calculated fitness and evolved structure, the number of these individuals called evolution size. Here, the yellow individual describes an initial or saved individual, and the orange individual describes a novel individual. In the initial process, initial individuals are generated in the global landscape uniformly. These individuals will be calculated fitness after generation. In the evolution process, the whole population is divided into several clusters. The number of clusters is the number of saved individuals. By calculating the correlation coefficient between distance and fitness in each cluster, we can evaluate the local landscape complexity. Then, we investigate the 2 parameters, correlation coefficient and the best fitness. In each 2 clusters, the whole population can be evolved effectively. In the algorithm net NEAT, an individual is a genotype of neural network. It includes node ID, connection, information, weight, and BIOS. which can be recorded as an adjacency matrix we call the feature matrix. Between two feature matrices, we use Euler distance to distribute the correlation between them, also two individuals. Here, we describe how to generate a novel individual by global search. We reported two kinds of search methods, binary search and golden section search. We obtain the feature matrix of global individual by superposing the two feature matrices. For the local search, we use the original search design of NET. The usage timing of global search or local search should be further discussed. We used cluster method to divide all the individuals into several clusters. The number of clusters is the number of initial or saved individuals. And then we can evaluate the local landscape complexity of each cluster. Correlation coefficient can be used to evaluate the local landscape complexity. After dividing the whole population, individuals with best fitness will be opted in each cluster. In the unimodal landscape, the difference at the distance between each individual and the best individual are absolute negative correlations. We call it positive rho. For the multimodal landscape, the relationship between the above two kinds of value is not significant. For searching selection are based on correlation coefficient as the best fitness in each cluster. Please see our paper for getting detailed information. The above 10 pages illustrate our proposed strategy, BiNet and GSNet. Here, we designed 3 types of experiments to verify the effectiveness of reverse encoding tree. In the landscape evaluation, we discuss how our proposed and cutting-edge evaluation strategy finds the maximum value in 2 types of fitness landscape. In the benchmark evaluation, we select logic genes and 2 continual control gaming benchmarks in the OpenAI gene for discussing the performance in NET and NET with reverse encoding tree. In the noise evaluation, we discuss 3 types of noise in the above 2 types of strategy. Here, I will speak to discuss landscape evaluation, which includes the dataset of mountain Everest and the fitness speed in each strategy. It is shown in supplementary materials in our paper. In this presentation, I'm going to report on the result of the last 2 experiments. In the benchmark evaluation, we see 3 environments: Logic Gene, Cartpole version 0, and Lunar Lander version 2. Logic genes are the basic environments for evaluating the learning ability of neural network. Cartpole version 0 is a classic environment of reinforcement learning. In its environment, there is a small cart which moves on the one-dimensional track without any resistance. The movable pole is connected to the cart, which will switch left or right inertially. We need to control our cart to move so that the pole can keep balance. Lunar Lander version 2 is a simulation of lunar landing, the environment of which is more complex than that of Cartpole version 0. By controlling the left, right, and bottom engines, the ship will fall into the selected area with the right direction. In addition, we further clarify the experimental parameters. Here, The iteration distributes the repeats on one experiment, and the evolution size means the number of individuals which need to be evolved structure and calculated fitness in each generation. Evolution size can measure the calculation times in each generation, which is different from population size. In this presentation, we showed our raw data on the right side. We can see the peaks of our proposed strategy and the baseline, net and FSNet. From implied task to actual task, the task complexity are increased gradually. With the increase of task complexity, the performance of our proposed strategy will better and better. The results in reinforcement learning experiments, Cartpole Version 0 and Lunar Lander Version 2 are also interesting. Because local peaks are small and sharp, the evolution speed of evolutionary strategy depends on the location of the initial population largely, and the difference in performance between our proposed and the baseline will be greater. In the noise environment, we see three types of noise: normal random noise, reverse noise, and Gaussian noise. We see noise evaluation in the environment of Cartpole Version 0. In the normal random noise, we set the minimum value 0.05 and the maximum value 0.1. The noise value will be randomly selected in the closed interval between them. Reverse noise maps the original observation data received. Since 100% of the noise environment is consistent with a noise-free environment. So, we dilute the noise level to the original 50%. Gaussian noise is a common interference in sensory data. We set up it by computing the variance of all recorded states with a means of 0. Field rate represents the probability that the algorithm cannot finish the task. The result shows that in the set of normal noise, the field rate of BiNet and GSNet are not increased. In addition, under the reverse noise and Gaussian noise, they increase rapidly after 30% and 70% respectively. The baselines increase significantly at the beginning under all types of noise. For the strategies we proposed, the difference between them is not obvious, and the maximum difference is only 0.4%. Here, we reported an evolutionary strategy named Reverse Encoding Tree. Past landscape evaluate, together with other well-established evolutionary strategy. Reverse Encoding Tree showed the faster evolution speed in this case. In addition, we created two net algorithms based on Reverse Encoding Tree. We evaluate them in logic genes, OpenAI gene, and noise environment with the baseline net and FSNet. The results show that nets with reverse encoding tree have higher performance and stronger robustness. Here are the acknowledgements of this work. Please read our paper for obtaining more detailed information. Moreover, the source code and raw data are open source with a link on this page. Thanks for your listening.